Hello everyone. In this problem, we're presented with a polynomial and we are going to use derivatives to help us sketch the graph of this polynomial. All right, so I don't really have all the homework problem written down here. I'm going to do that as we go. So our goal is to sketch the graph. Now, I'm not focusing on the x-intercepts, but clearly this one's sort of an easy one to find the x-intercepts because it's already been factored. But okay, but what I'm going to focus more on is calculus and how calculus can help us to sketch the graph. And so I'm going to start off with finding the critical numbers. So we're trying to sketch the graph and we're going to use calculus to do that. So we'll find the critical numbers and let's see how that goes. So the critical numbers are where the derivative is equal to 0 or numbers in the domain of f where f prime is undefined. Now, for this problem here, in order to take the derivative, I use the product rule, and I sort of drag this out a bit just to show that what I am using is the product rule. So I take the derivative of the first factor, which is x, and that derivative is 1. I leave the other factor alone, then I leave x alone and take the derivative of x plus 2 cubed. And then I'm going to set that equal to 0 and solve. I am going to factor out x plus 2 squared, which will leave behind x plus 2. See, x plus 2 squared times x plus 2 is x plus 2 cubed. And it will leave behind 3x. So that becomes x plus 2 squared times 4x plus 2. And that becomes 2 times x plus 2 squared times 2x plus 1. So when I find the critical numbers, I solve by setting the derivative equal to 0. And that's pretty straightforward, given that I've already factored this. So that gives x plus 2 is 0, 2x plus 1 equals 0, so x equals negative 2, x equals negative 1/2. All right, and one hopes at least I hope I did that right. And then B, we're going to make a chart showing where f is increasing or decreasing. And part of the goal of that will then be for us, or part of the reason we're doing that in part, is so we can determine whether these critical numbers correspond to a local max or local min, or absolute max or absolute min. So we have these critical numbers, and what the critical numbers mean is that at those points, where x is negative 2 and x is negative 1/2, the tangent line is horizontal. But that does not tell us right off, just given that, whether we have a local max or a local min. And what I can do is I'm essentially making a sign chart, which not sine and cosine, but a sine positive negative for the derivative function. And what I do is I'm trying to determine on which intervals the derivative is positive and which intervals the derivative is negative. And the sign chart works with an idea of having a number line where let me say maybe partition the number line by, well, maybe not partition, but I break up the number line, or the real numbers, by these critical numbers. And then I ask myself, when is f prime positive and when is f prime negative? The reason I'm doing that is so I can draw a conclusion about the function f and where f is increasing or decreasing. Now, 2 times x plus 2 squared is never negative because it says it has squared. That's negative, never negative. It's equal to 0 when x is negative 2. Oops, I did exactly opposite. It's never negative, so I need to put plus. Now, 2x plus 1, if I plug in x is negative 4, x is negative 3, I get negative. If I plug in x is negative 1, sort of left that off here. If I plug in x is negative 1, I get negative. But then at negative 1/2, I get 0. And after that, the function turns positive. And what I see for f prime is I multiply these two factors, because f prime is the product. Let's just make clear that that's what I'm doing there. F prime of x is the product of these two factors, 2 times x plus 2 squared and 2x plus 1. So f prime is the product of those factors. Now, if I multiply the positive and negative, I get a positive negative is a negative. A positive negative is negative again. Positive positive is a positive. Notice how the sign as we cross over negative 2 does not change. And that is because it's x plus 2 to the second power. So when I look at my chart, that repeat, negative, negative, that corresponds to crossing over negative 2. And negative 2 goes along with x plus 2 squared. Because it's squared, it doesn't flip in sign. But at negative 1/2, we go from negative to positive. That happens because 2x plus 1 is raised to the first power. And therefore, as we see, 2x plus 1 flips from negative to positive, negative 1. And then what do we say about f? F is decreasing. Why is it decreasing? Because the first derivative is negative. And then it decreases again as we cross over negative 2 because the first derivative is negative. And then at beyond negative 1/2, f is increasing because the first derivative is positive. So what we see then, or what we're going to conclude, is that x equals negative 1/2, we have a minimum value for the function. While at x equals negative 2, it's true it's a critical number, so you have a horizontal tangent line, but the derivative, it doesn't correspond to a minimum or maximum. We have a horizontal tangent line, but it's not a minimum or maximum. Essentially, well, I sort of can look ahead, sort of ruining it, but it's going to be, I'm going to be decreasing and it's going to be flat, and then I'll start decreasing again. That looks a bit like y equals x cubed, which actually isn't surprising because that's our function. I could have predicted that. It's x plus 2 cubed. But it would be like x plus 2 cubed, but flipped over, like negative x plus 2 cubed. And then, but then anyway, then after that we have a minimum. So do you see why? What I'm getting at is that you have a critical number which leads to a horizontal tangent line, and another critical number that leads to a minimum. I mean, that's a rough sketch, but we're going to get something like that. All right, then we're going to move on to the next part, which is we're going to look at where f is concave up and concave down, and in order to do that, we're going to find inflection points. So the inflection points are found by finding the second derivative and setting the second derivative equal to 0 and solving. Now, as I look at this, I'm thinking, well, I'm going to have to take the derivative of f prime to get the second derivative. And I was thinking, while I was doing that, about whether I can see some clever way to do that. But I guess I'll just charge ahead and use the product rule once again. So when we find inflection points, we find the second derivative. Then we set the second derivative equal to 0 and solve. All right, I feel like maybe I can just go a little faster. I'm using the product rule. So for the first factor, which is x plus 2 squared, I'm going to take that derivative, which is 2x plus 2 to the first power. So that's the derivative of the first factor. And then I leave the second factor alone. I don't take that derivative. And then I add, well, I'm going to leave the first factor alone, and I'm going to take the derivative of 2x plus 1, which is 2. So I hope that made sense to everyone. Let's see what I get. I'm going to multiply 2 times 2 and get 4 times x plus 2 times 2x plus 1 plus 4x plus 2 squared. Now, if I multiply this out, this will be a quadratic, and I can just factor. But I notice that I can already, from the beginning, without multiplying it all out, I can factor a 4 out and an x plus 2 out. So I think it makes it a little faster if I do that. And left behind is 2x plus 1 and a 2x and an x plus 2. So that was at least 4 times x plus 2. And then I have 2x. I could see someone not thinking that's very neat. Having a hard time reading that. I have 2x plus x makes 3x. 1 plus 2 makes 3. And I can factor that out. I can factor out a 3. And so that's the second derivative. And now I solve f double prime of x equal to 0. So that means that I'll have 12 x plus 2, x plus 1 equal to 0. So x equals negative 2 and x equals negative 1. And then those are inflection points. Okay, I'm going to highlight those inflection points. But I'll also highlight the second derivative. Oh, where's that? Maybe I'll put it like that. It doesn't actually, it doesn't look as good there. Maybe I'll just, the way I wrote it, I'll just highlight it here. But 4 times 3 is 12. So it's 12x plus 2 times x plus 1. Okay, now I'm moving on to part D, which will be that we are going to make a chart showing where the function f is concave up and concave down. And in order to do that, what I'm going to do is I'm going to make like I said, I'm going to make a chart. Okay, so I had to go to the next room because of someone came in and wanted to play video games, so I had to leave. Oh well, all right. So I'm going to do the same type of chart as I did before. And here's f double prime, and I'm going to write those factors of f double prime, which are 12 times x plus 2, and then I have x plus 1. And then I'm going to just plug numbers in for the interval to this guy here. Let's try orange. X plus 2, if I put in negative 4 is negative, it just goes negative. And then until I get to negative 2, negative 2 plus 2 is 0, then I get positive. And then x plus 1, it's negative when I put in negative 4, negative 3, negative 2, and then it becomes positive as I cross over negative 1. So I just fill in negative, negative makes a positive, positive, negative makes a negative. Now I make a statement about f. This is about concavity, and now I was supposed to write down as directions here. So make a concave up, down chart. All right, now F double prime positive means that F is concave up, F double prime negative is concave down, F double prime positive means F is concave up. And what are those, again, what are those, like, those partition points or dividing this, or the number line, those which make those vertical lines? They're not vertical asymptotes. Those are correspond to x equals -2 and x equals -1, which are those are inflection points. Then what we're going to do is simply plot points. Now, if you're just not using calculus at all, you just plot points anyway and see how it goes. But we're going to specifically plot critical points and inflection points. Now, the thing is that usually for most of these problems, I'm not going to find the x-intercepts, but it's just sitting right in front of us. So I think we should. But actually, the x-intercepts I think are going to correspond with maybe other things that we found before. So meaning inflection points. Maybe, let's see. This is x times x plus 2 to the third power was our original function. So, I mean, the reason when we use calculus here in this section of the calculus book to sketch the graph of the function, it does not focus at all or talk really much about x-intercepts. That's sort of a pre-calc idea. But if you have it factored, why not? Now this is x equals 0, and the multiplicity of that 0 is 1. And then x plus 2 equals 0 gives x equals -2. And we see the multiplicity of that factor is 3. Essentially, what this happens with f of x is near its x-intercept, say when we get close to x equals 0, this graph is going to look like a line, because if you put in 0 for x, for this part x plus 2 cubed, you have 0 plus 2 cubed is 8. And so near x equals 0, the graph looks a lot like 8x. Now, when x gets next to -2, x is -2, and then the graph looks a lot like -2 times x plus 2 cubed. You can do a lot without calculus actually on this graph. So as x approaches, if x is really close to -2, then you have -2 times x plus 2 cubed, and so the whole thing looks like a quadratic. I mean a cubic. Okay, and so let's just then go ahead and plot points. So, I mean, we already have our x-intercepts. So we have 0, 0, and we have -2, 0, our x-intercepts. And I bothered to write down the multiplicity, because actually that will help us. But let's just plot points, which are, what I mean by that is I'm going to start by plotting, starting our inflection point, which is also a critical point, and it's an x-intercept. So we have a critical number, which is an inflection point, and that was at -2, and we got -2 times -2 plus 2 cubed, which is 0. So we already have that 0, 0. We already did that when I found the x-intercept. Okay, what else do we have that we can plot? We can plot a minimum and another inflection point. Let's do this other inflection point. And so I'll have f of -1 equals, right, it was -1, wasn't it? So we get f of -1 is going to equal plugging into our function. It's important for us to understand that we're putting numbers into the function, not into the derivative. So I'll get negative 1 plus 2 cubed, which is negative 1 times 1 cubed, which is negative 1. So we get the point negative 1, negative 1. And then we had, I have to look at the picture. I mean, the things I drew those pictures, and I can't really do it. Unfortunately, I can't do a side by side on this graphing program. But we have a minimum at negative 1/2. That's what we found out from our chart here. That we had the negative 1/2 corresponds to a minimum, and x equals negative 2 is neither a max or the minimum. That's why I wrote minimum or neither. And then I have also these inflection points. Okay, so f of negative 1/2 will be a good one. So that is a min. And so that'll be negative 1/2 plus 2 cubed, which is negative 1/2 times 3/2 cubed, which is negative 1/2, 27 over 8, and that's negative 27 over 16, which, you could write as a mixed number. Well, why not try it? That's 16 goes into 27 one time. That's not that difficult, but I guess it's going to be negative 11 over, it's going to be negative 1 and 11/16, right? 11 plus 16 is 27. So, it's like negative 1 and 2, and I mean, if this is, and what would that be? Negative 1 and 3/4. If this is 12 over 16, 12 over 16 is 3/4. So it's like negative 1.75. I mean, roughly speaking, it's obviously between negative 1 and negative 2. And so let's go ahead and at least plot those points, but then let's just see whether calculus really does help us. Well, it certainly does, but whether I can put this all together and make sense of what I wrote down on those charts. So f of negative 2 is 0. Well, I knew that already just from the function was factored, and so I could easily find the zeros. Then I have another point which is negative 1, negative 1. Okay, that's an inflection point. So these are both inflection points. And then we have a minimum value which is at negative 1/2, and then around negative 1 and 3/4, and that's our minimum value. And so that's a little bit cramped. Okay, so let's try to, problems I can't, that's okay, we have to go up above here. I can't do a split side by screen. But see, look, the function decreases and then decreases again as I cross negative 1/2. And then it increases, no, as I cross negative 2. Decreases until I get to negative 2, and then it has a horizontal tangent line, decreases again, and then at negative 1/2 I have a minimum. So at least I know that negative 1/2 is a minimum. And then it's decreasing, okay. But to the left of negative 2, I know it's concave up. So what the graph looks like is it's decreasing and it's concave up. It looks something like this. Let's make it more dramatic by making a bolder line. And then we have a horizontal tangent line there also, because negative 2 is an inflection point. And then what happens if you look between negative 2 and negative 1, it's concave up. And so that's what happens on the inflection point. It switches. And how does that look? It looks a lot like x plus 2 to the third power times a negative number. That's what it looks like. And I feel like maybe I didn't really even quite illustrate or show well enough that idea of a horizontal tangent line. I want to really get that in there by doing something like that. And then it becomes concave up again past negative 1, because that's an inflection point. Oh, and then what was it? We found out the zero. No, what was the other intercept? The other intercept is zero, which was, it's always good to have the y-intercept anyway. If you get the x-intercept. Okay, the problem is it just doesn't look as good as I think it could, but it's not that bad either. I mean, there's a whole question of, well, why would anybody want to do this if you can just use your calculator? Well, we're supposed to be analyzing functions and trying to understand what functions do. The thing is, I'm using a little drawing technique that's maybe not so good when I'm trying to do scientific graphs. Like maybe if I were teaching some sort of like an art class, I would do this sort of rough, sketchy look thing that looks sort of rough, but I don't want to do that when I'm doing, that art look for this type of drawing. I want it to, and I certainly don't mean to say that art look is bad in general, but for this one, I want a certain clean line look, which I don't think I necessarily achieved at all. Alrighty, so did I label well enough? I would think that maybe if I put these numbers on the top, it's messy looking. But is it so bad that it's messy looking? And then maybe, but it is hand drawing. Okay, and so the thing is, it would be even better if I can fit in these values. You could fast forward the video, right? Or you could put it so that it goes at 1.5 the speed, maybe. Inflection point, minimum. I think you can see by the way I'm drawing it, hopefully, where it's concave up and concave down. And also what I want to emphasize and show is that the graph continues to go up. So what that idea is, by showing that it's going up, is telling us what they call the end behavior. The behavior as x goes to infinity and x goes to negative infinity. For polynomials, it's either just going to keep going up or going down. You don't have horizontal asymptotes with polynomials. And so I want to indicate that. I don't want to just stop down sort of lower. And you can even plot some other points pretty easily. Like you could put in 1, but when you put in x is 1, you get I think 27. So all right. Actually, I have somewhere else the solution. Could just sort of sneak over and look at that. Not the solution, like I just have the one I did on a calculator. Um, but I shouldn't necessarily do that. But now I feel like I'm stuck doing it since I started. Which one was this? Is this it? No, these are other solutions. Okay, so here is another look at that. Could even take a picture of that and insert that, right? How can you do any of this online stuff without an iPad? Is it too much for me to say something like that? I mean, but it just seems like iPad is what we need these days during this online stuff. I feel like I did a lot of work there, but I would be disappointed if I, say, got one of these numbers wrong. It'd be a real bummer. Anyway, it looks pretty close to what I did. Here, when I have this picture here, I didn't do it, so I made the x and y axis um, the, um, to scale. Oh, okay. Yeah, got these numbers here, same. It looks super neat. I should post those solutions also. Okay, hand drawing's not so bad, or is it? The thing is, when I'm drawing, it sort of doesn't look like this passes the vertical line test. Be careful of that. You don't want to do something that doesn't pass the vertical line test. I mean, obviously that's a big no. It has to be a function. But I was showing that it gets really steep. But then what happened is I overdid it. It's not so steep that it becomes a vertical line. That would be silly. It's not a vertical line. It just gets super steep. Alrighty? Okay. I think I'm making it worse. I better just quit while I'm ahead. Alrighty. Okay. Well, you're ahead. All right. So, again, this is the graph of f of x equals x plus 2 cubed. All right, that's all. Thank you.